So, let's talk about why we should lean towards an event loop for our IO-bound tasks. It's all about scalability and resource management.
But what about the complexity of implementing an event loop compared to a thread pool?
Complexity is relative. With modern frameworks like Node.js or Python's Asyncio, you get a lot of that handled under the hood. Plus, managing threads can be more complex due to context switching and synchronization issues.
What if our tasks are very CPU intensive though? Wouldn't a thread pool be better suited then?
True, for CPU-heavy tasks, a thread pool would make sense because each task can run on its own core. However, with I/O-bound tasks, you don't want to tie up threads waiting for I/O operations to complete. That's where an event loop shines. It handles those waits efficiently without blocking.
And how does this affect our choice when it comes to handling concurrent requests in our app?
Well, with an event loop, you can handle thousands of concurrent connections using just one thread by asynchronously waiting for I/O operations. This means lower memory usage and fewer context switches. In contrast, a thread pool might require creating multiple threads per request, which could lead to higher overhead and potential performance bottlenecks at scale. Speaking of which, let's dive into the performance implications. An event loop can significantly reduce latency and improve throughput for I/O-bound tasks, because it doesn't waste time on context switching between threads.
That makes sense. But how do we measure these improvements in real-world scenarios?
Good question. You'd typically look at metrics like response time, throughput, and resource utilization. For instance, an event loop might show lower average response times and higher throughput for a large number of concurrent connections compared to a thread pool.
And what about memory usage? How does that compare?
Memory usage is another key factor. An event loop generally uses less memory since it operates with fewer threads. Each thread in a thread pool consumes resources, so having many threads active simultaneously can lead to higher memory consumption.
So, if we're dealing with a highly concurrent system, an event loop seems like the better choice?
Absolutely, especially if your application is I/O bound. The reduced overhead from fewer threads means you can handle more requests with the same amount of resources, making your system more efficient overall. Exactly. Now let's talk about scalability. When it comes to scaling your application, an event loop can be a game changer. It allows you to handle a large number of simultaneous connections with minimal resources.
That sounds promising. But how does this play out in terms of horizontal scaling?
Horizontal scaling is where both models can excel, but in different ways. An event loop can scale well within a single process, making it easier to manage and maintain. However, when you need to scale across multiple machines, the simplicity of the event loop architecture can still offer advantages in coordination and communication overhead.
So, the event loop simplifies things on a single machine. But what about load balancing and distributing workloads?
Great point. With an event loop, you can design your system to distribute tasks more efficiently because each task runs asynchronously without blocking others. This means that even as you add more machines, the asynchronous nature helps in balancing loads effectively. In contrast, a thread pool might require more sophisticated mechanisms to ensure efficient distribution of tasks across multiple threads and processes.
And how does this impact maintenance and debugging down the line?
Maintenance and debugging are indeed important considerations. Asynchronous code can sometimes be harder to reason about initially, but once you get used to it, the benefits outweigh the initial learning curve. Plus, modern tools and frameworks have improved significantly in helping developers debug asynchronous applications. On the flip side, managing threads can introduce complexities like deadlocks and race conditions, which can be tricky to diagnose and fix.
Makes sense. So, for long-term sustainability and ease of management, an event loop seems preferable for our use case.
Definitely. The simplicity and efficiency of an event loop make it a robust choice for scalable systems, especially given the nature of I/O-bound tasks we're dealing with. Right, so let's shift gears a bit and talk about memory usage. When it comes to memory, an event loop generally uses less because it operates with fewer threads.
That makes sense. Can you elaborate on how exactly the memory footprint differs?
Sure, each thread in a thread pool consumes a significant amount of memory for its stack and other overhead. With many threads active simultaneously, this can add up quickly. In contrast, an event loop manages everything with a single thread, reducing the total memory overhead significantly.
And how does this affect our choice when we're dealing with limited resources?
Limited resources definitely favor an event. By minimizing the number of threads, you reduce memory consumption, which is crucial when you have constraints. This also means you can handle more concurrent connections without running into out-of-memory error.
What about garbage collection and memory management? Does that differ between the two approaches?
Garbage collection can vary depending on the language and runtime environment. Generally, with fewer threads, there's less pressure on the garbage collector, leading to more predictable performance. In a thread pool, frequent context switching and creation of new threads can put additional stress on garbage collection routines.
So, in environments where memory is at a premium, an event loop seems like the way to go.
Absolutely. The reduced memory footprint of an event loop makes it particularly suitable for such environments, ensuring that your application remains performant even under tight resource constraints. Let's talk about the concurrency model differences now. Event loops and thread pools handle concurrency quite differently, which impacts how tasks are managed and executed.
How do they differ in their approach to handling multiple tasks concurrently?
In an event loop, tasks are handled asynchronously and non-blocking. Each task runs until it needs to wait for I/O, at which point control is returned to the event loop so other tasks can run. This is ideal for I/O-bound operations where most of the time is spent waiting.
And how does this compare to a thread pool?
A thread pool uses a set of worker threads to execute tasks concurrently. Tasks are distributed among these threads, and each thread runs a task to completion before picking up another one. This model works well for CPU-bound tasks where parallel processing speeds up execution.
So, the key difference lies in how they manage waiting states and task execution?
Exactly. The event loop excels at managing tasks that involve lots of waiting by interleaving them efficiently. On the other hand, a thread pool is better suited for tasks that require heavy computation because each thread can fully utilize its CPU core without being blocked by I/O waits.
That makes sense. So, choosing between them really depends on the nature of the tasks we're dealing with.
Precisely. Understanding whether your tasks are more I/O-bound or CPU-bound will guide you toward the best concurrency model for optimal performance and resource utilization.